Welcome to all in the new lecture in the graph that is on walk and path. So here we will discuss about the what is the walk in a graph and the path. So first of all, what is a walk? In a graph theory, a walk is defined as a finite length alternating sequence of vertices and edges. We all know that what is the graph? Graph is the made of vertices and the edges. So what is walk? Walk is a finite length between the vertices and the edges. And the total number of edges covered in a walk is called as the length of the walk. So let's take an example for this. Suppose we have the graph is like that, and here we have the vertices, 5 vertices are there, A, B, C, D, E. So if we consider here, suppose this is this walk A, B, C, E, D. So you can see that A, B, C, D, C, E, D. So what is the length of this walk? Actually, this is a walk, right? We include here the vertices and the edges. But what is the length? Length is the number of edges. How many edges are included in the walk? So A, B, C, E, D. How many edges are included here? 4. It means that the length of this walk is 4. Next, suppose our walk is D, B, A, C, E, D, E, C. So this is also a walk. And what is the length of this walk? Because here we have included the 7 edges, it means that the length of this walk is 7. Next, if we talk about this walk E, C, B, A, C, E, D. So how many edges are included here? Here we have total 6 edges are included in this walk. So the length of this walk is 6. Right? What is the walk? Now we have the two types of walks are there, open walk and the closed walk. So first of all, what is the open walk? A walk is called as an open walk if length of the walk is greater than 0. What does it mean? Length of the walk is greater than 0. It means that we have some length is there. Means some vertices and some edges are there. And second one, the vertices at which the walk starts and ends are different. So our walk is open walk if our starting vertex and the last vertex and vertex is different. And closed walk, a walk is called as closed walk if length of the walk is greater than 0. And second one is the vertices of at which the walk is starts and end points are same. So in open walk, the starts and end points are different, and in closed walk, starts and end points are same. So that is called the closed walk. One note is here. You have to remember these points. First of all, if length of the walk is 0, right? Here we say that length of the walk is greater than 0. So if length of the walk is 0, then it is called a trivial walk, right? And both vertices and edges can repeat in a walk whether it is an open walk or a closed walk. So if we talk about the open walk or closed walk, doesn't issue, but in walk, if we say that walk, so in walk we can repeat any edges or vertices, doesn't issue are there. So that is called the walk. Now second one is path. So what is the path? In graph theory, a path is defined as an open walk. So you see here, concentrate on this point. A path is defined as an open walk in which neither vertices are allowed to repeat except possibly the starting and the ending vertices. So leaving the start and ending point, no one vertex is allowed here to repeat in path, and nor edges are allowed to repeat. Neither vertices nor edges can be repeat in the path, only accepting the starting and the ending vertices. Now come to the cycle. So what is a cycle? A cycle is defined as a closed walk in which neither vertices are allowed to repeat except starting and the ending vertex, and nor edges are allowed to repeat here. But that is a closed walk, right? So if we have the closed walk and no vertices and edges are repeated, so that it become a cycle. If we have an open walk and no vertices and edges are repeated in our walk, so that is called the path. Or you can say that a closed path, right? Closed path, so that become a cycle, right? So we can say that a closed path is a cycle. Next one is come to the trail. So what is trail? A trail is defined as an open walk in which vertices may repeat, but edges are not allowed to repeat. So that walk is called the trail if it's an open walk, and here vertices may be repeated but edges are not allowed to repeat. Next one is circuit. So what is the circuit? A circuit is defined as a closed walk in which vertices may be repeated but the edges are not allowed to repeat, but that is a closed walk. Or in another way you can say that a closed trail is called as a circuit, right? So you have to remember all these points clearly, right? Now, one notice here, you have some points, important points, you have to remember this. Every path is a trail, but every trail not be a path. It's clear? Why? Because every path is a trail. We say that every path is a trail because in path, vertices and edges are not repeated. But in trail, vertices may be repeated, but edges are not repeated. So like that, every path we can say that become a trail, but every trail not be path. Why? Because in trail, vertices are repeated, may be repeated, but not in path. Right? Next one is every cycle is a circuit, but every circuit need not be a cycle. Same here, because in a cycle, we have that no edges are repeated, should be repeated, and not uh, vertices not may be repeated. But in circuit, vertices may be repeated but not the edges. So we can say that every cycle is a circuit, but every circuit need not be a cycle. Next one is for direct. If we talk about the directed graph, so in directed graph, we put term directed in front of all the terms defined above, right? Means directed trial, directed circuit, directed cycle, like that only in the directed graph. Now, in a you have to remember in the form of chart all these definitions which we study here. So in this graph, you can see that first of all we have the walk, right? So what is walk? Walk in a graph theory, if or walk, it means what is walk? Any vertices or length, any vertices and connected to any edges, that become a walk. So but when walk, if no edges are repeated here, vertices may be repeated, so what that walk would become the trail. And if our walk is like that in which no edges and no vertices are repeated, so that become a path. After that, if our trail is closed, so we can say that become a circuit, and if our path is closed, so we can say that become a cycle. And we can say that every cycle is a circuit, but not circuit is a cycle. And similarly, we can say that every path is a trail, but every trail is not a path. So by this chart, you can see all the definitions and you can remember it. So you remember this chart, then you have to be easy. Now let's take some examples for this about the walk and path. So suppose we have this graph, it is given that, and here we have the vertices, 7 vertices are there, A, B, C, D, E, F, G. So what we have to do here, decide which of the following sequences of vertices determine walks. For those are walks, decide whether it is a circuit, path, cycle or a trail. So first we have to see that become a walk or not. After that, if that is a walk, then we have to decide that is a circuit or a path or a cycle or a trail, right? So first of all, suppose we have this A, B, G, F, C, B. Suppose, so you can see this become a walk or not. A, B, G, F, C, B. Yes, yet this become an a walk. So this is an a walk, but which type of walk is this? This is a trail, right? Why trail? Because in this we have edges are repeated. B edge is repeated here, but sorry, B vertex is repeated here, but not any one edge is repeated. So we can say that that walk is a trail, right? Next one is, suppose we have this one, B, G, F, C, B, G, A. So this is also become an walk, but which type of walk is this? Here you can see that our vertices are repeated here, right? B and G. B and G vertices are repeated here. B, G, F, C, B, G, A, right? So it become a walk, right? And now next one, C, E, F, C. So C, E, F, C. C, E, F, C. So it is also a walk. But which type of walk is this? C, E, F, C. C, E, F, C. Here for starting and the last point are same only. Vertex is same. Note edge is repeated. So what is become? It becomes a cycle. Right? It becomes a cycle. Now next one is C, E, F, C, E. C, E, F, C, E. Right? So here it is again become a walk, and but here the not the first and last point are not the same, so it is a simpler walk. Now A, B, A, B, F, A. B is not connected to F, right? F is not connected to directly connected to A, so it is not a walk, right? It's not become a walk. Clear it? Next, suppose we have this F, F, D, E, C, B. So what is this? F, D, E, C, B. This is a walk, and which type of walk this is? Path, right? Because its first and last vertex are not the same, and not edges are repeated here, not vertex is repeated here. So this become a path. Clear it? Now let's take another example. Here if we have, suppose this graph is given, this is the directed graph, you can see this, and here we have the 5 vertices are there, x, y, u, v, w, right? So if we consider here these walks, so you have to give some questions answers here. If we have this one, so you have to first check that all of these A, B, C, D walks, which of the given sequences are directed walk, because this is a direction. I told you that if we have the directed graph, so just we simply initially before that any name we can represent it by the directed, right? So here we have to see that this has become a walk or not. So which of these out of these 4 points that becomes a directed walk? So you can see here x, u, y, w, x, u, y, sorry, x, v, y, w, v. Yeah, it's become a walk, right? It's become a walk because x, v, Vy, Yw and Wv. Yeah, directions are right. It means they become a walk. Next, B, we see that X, U, now X, U, now X. So it becomes again a walk, right? Next, C part, we said see that X, U, V. But U is not connected to V. So it is not become any walk, right? Because U and V are not connected. So the D part, X, X, V, Y, W and U. No, sorry, W, V, again U. So V vertex is not connected to U vertex. It means that is not become any walk. Clear it first one. Second one, what are the lengths of the directed walks? So you can check that how many edges are included here in this walk. So that will be the length of the walk. Third one, which directed walks are also directed path. So just we have to see that which walk is become a path, right? So which walk become a path? First of all, we have to discuss only A and B because only A and B are we have the walk. These are not the walk. So now we have to check only the A and B option here. So which become the directed path? Because here you can see that no vertex is repeated here, right? So it become a path. But here we have the vertices are repeated, so it's not become a path. Which directed walk are also directed cycles? So directed cycles. So what is the directed cycles? That is become here. So you can see here in the first part only A and B are directed walks. I told you that, and C is not the directed walk since there exists no arc from vertex U to vertex P. Similarly, D is not a directed walk. Why? Because there is no arc from vertex V to vertex U. Now in the second part, I told you that both the directed walks A and B that have length 4 because the edges in both the walks are 4. Third one is neither A nor B are directed paths, right? Neither A nor B are directed paths here. And why this is because vertices repeat in both of them. In both of them, vertices are repeated. It means that that node become a path. Vertex V repeats in walk A and vertex U repeats in walk B. Right? So it's not become a path. In fourth one, neither of them are directed cycle. No one is a directed cycle. Why? Because in all we have the vertices repeated or the edges are repeated. So no one cycle can be made here. You can see here walk A does not represent a directed cycle because its starting and ending vertices are not same, and walk B does not represent a directed cycle because it repeats vertices and edges. Right? Now we have another example. Here we have suppose this graph is given. So observe the given sequence and predict the nature of walk in each case. Here our vertices and edges are given here. So now first of all if we say that this walk V1 E1 V1 E1 V2 E2 V3 E2 V2 E2 V2. So what is this? This is a walk, or you can say that that is a open walk because the first and the end vertex is this is different. So this become an open walk. Next, if we have this walk V4 E7 V4 E7 V1 E1 V2 E2 V3 E3 V4 E4 V5, right? So what is this? This become a trial. Why? Because here it become not a path because vertex V4 is repeated here, right? Next one is if we have this V1 E1 V2 E2 V3 E3 V4 E4 V5. So what is what this has become? This has become a path, right? Because no vertex is repeated here, no edges are repeated here, so it becomes a path. Next one is V1 E1 V2 E2 V3 E3 V4 E7 V1. So what is it? It become? It become a cycle. Why? Because only the starting and the ending vertex is same. Otherwise, no vertex is repeated here, no edges are repeated here. So it becomes a cycle. Next one is V6, E5, V5, E4, V4, E3, V3, E2, V2, E1, V1, E7, V4, E6, V6. So what does it become? It become a circuit, not a cycle. Why? Because vertex V4 is repeated here. That is the middle vertex between the vertex of the walk vertex. So it does not become a cycle. It become a circuit because first and the last vertex is same here, and here vertex is repeated. So it become a circuit. Clear it? How to define the walk and how to define the path in this. So now today's lecture is completed now.